Okay, in activity 3 we're going to be using the logic gates that we've used in the previous activities, and we're going to be designing a circuit that follows a specification. So, a logic system has two inputs, A and B, and two outputs, X and Y. So in this case, if we have two outputs, we're going to need an additional output circuit. Therefore, you are going to have to combine logic gates. So this is our specification. If no switch is pressed, both X and Y will be at logic level 0. If only one of the switches is pressed, X will be a 1 and Y will be a 0. And if both the switches are pressed, then X and Y will both be a logic level 1. Well, we have two inputs, A and B. All the combinations of those inputs are 0, 0, 0, 1, 1, 0 and 1, 1. And it says, if no switch is pressed, both X and Y will be at a logic level 0. Well, the only time when no switches are pressed is when A is a 0 and B is a 0. So therefore X is a 0 and Y is a 0. If only one of the switches is pressed, X will be a 1 and Y will be a 0. Well, here only A is pressed, therefore X must be a 1 and Y must be a 0. And on the next line, only B is a 1, therefore X must be a 1 and Y must be a 0. Finally, it says if both switches are pressed, then X and Y will both be at logic level 1. Well, on the last line, A and B are both pressed, and therefore X and Y must be a logic level 1. If we look at these truth tables, and let's break them up now, let's look at Y. When we go back to our original activity experiments, you will recognize that that is one of the particular truth tables, and it is the truth table for an AND gate. And then if we look at X, you should notice that that is the truth table for an OR gate. So what we're going to do, we're going to combine the inputs with these two logic gates to create two outputs, X and Y. So let's start with X. Now X is an OR gate, so let's draw ourselves an OR gate. There is our OR gate, and there is X, is our output. And A and B are both going to go to the input of that OR gate. Additionally, now looking at Y, we're going to need an AND gate. We have our output, which this is going to be Y. And we know that A and B are both going to go to the AND gate inputs. So all I'm going to do, I'm just going to continue drawing down there. So that is A going to that input. And here I'm going to continue this, and that is B going to that input. Excuse me. Now what do we need to do? We need to make sure that we can build that accurately, and the best way to do that is to label all the pins and the chips. Now this is an OR gate, so this is a 4071 chip, and this is an AND gate, and this is a 4081 chip. Our two inputs that we're going to use, we may as well use what we've used previously and know the numbers of. We're going to use pins 1 and pin 2 as our inputs, and we're going to be using pin 3 as our output. And the same goes for our 4081. Pin 1 and pin 2 as our inputs, and pin 3 as our output. So now I'm going to build that circuit. I need two inputs, A and B, which we already have, and I need two outputs, X and Y, so I'm going to need to build an extra output. And here I have, in blue Peter fashion, one I've prepared earlier. So I have my two inputs A and B, A on the right, B on the left, and I have my two outputs X and Y, not particularly mattering which way they go, and I've given them different coloured LEDs. So what does our truth table say is going to happen? When both switches aren't pressed, the outputs X and Y should be low. So turn on my power, and they are both low. When I press A, X should come on. I press A, and X comes on. I release A, and X goes off. When I press B, X should come on, and X comes on and off. And when I press A and B, both X and Y should come on. And there we go. X and Y have both come on. And when I've released both the switches, therefore they both go off. So we've designed a switch counter, i.e. what we're doing, when no switches are pressed, no lights are on. When one switch is pressed, one light is on. When one switch is pressed, one light is on. And when both switches are pressed, both lights are on. So it indicates how many switches are pressed at any one time. This is the end of activity 3. Welcome to activity 4, where we're going to design a comparator. Now this is quite a simple little design exercise, but it's quite nice because it involves combining different logic to create a particular single output. Let's look at our specification. So the logic system has two inputs, A and B. It has one output Q. Q is only at logic level 1 when A is the same as B, and when A and B are different, then Q is a 0. So first of all, let's fill in our truth table. So Q is only at logic 1 when A is the same as B. Well, where is A the same as B? Here they're both zeros, so Q is a 1. Here they are both 1s, so Q is a 1. And when A and B are different, then Q is a 0. Here they're different, and here they're different. Now, of course, the problem with this truth table is that, in fact, we don't have a logic gate that fulfills this, at least not within the criteria of our GCSE course. We recognise that this is actually an exclusive NOR gate. But we're not really meant to be using those in GCSE, so let's look at how we can combine logic to create an exclusive NOR gate. Well, if this doesn't fulfill the criteria for one logic gate, let's break it down. What logic truth table does it look like? Well, if we think about it, if that 1 was a 0 and we had 0, 0, 0, 1, what logic gate would that be? Well, it would be an AND gate. And if we took that last one to be a 0, then we would have 1, 0, 0, 0. And we know that that is a NOR gate. So maybe if we somehow manage to combine these gates together to create a single gate, maybe that would give us our answer. So what gate could be used to join both those together? Well, first of all, let's draw them out, because we know that we have A and B, and we are going to have a NOR gate in our circuit. So there is our NOR gate, and we know that we are going to have an AND gate in our circuit, and we know that A goes to both of our logic gates, and we know that B goes to both of our logic gates. And we have two outputs currently, and we want to feed them into one single logic gate. Now, what one would do that to give us a single output Q? Well, if we say it logically and look at it logically, if we had a 1 or a 0 here, that would give us a 1. So an OR gate would give us a 1 here. What would an OR gate give us here? Well, a 0, 0 would give us a 0. 0, 0 would give us a 0. 0 or a 1 would give us a 1. So in this case, our logic gate that we could put in between the outputs of these two is an OR gate. And that should combine to give us our single output Q. So label it all up. Pin 1, pin 2, pin 3. Pin 1, pin 2, pin 3. Pin 1, pin 2, pin 3. Again, the beauty of using similar logic gates here. We know that the NOR gate is a 4001. This is a 4081. And the OR gate is a 4071. So we've labelled it all up, and now we can build our circuit. Now, obviously, to save time, I've already built my circuit. I'm just going to show you a couple of fault finding exercises though. Always worth doing it whenever we turn on our circuit. So I have my 2 switch inputs A and B. I have my 3 chips which I've labelled for your convenience NOR gate, AND gate, OR gate. Because let's face it, they're all look exactly the same with the same number of pins and same inputs and same outputs. So it is worth labelling and making sure we know where we're going to go to. And we also have one output which in this case is labelled Q. Always check your power. So check pin 14 has power, pin 14 has power, pin 14 has power, pin 7 has power, pin 7 has power, and pin 7 has power. And then if we wanted to, we could follow our switches through. I've put switch A as white, so therefore if I go onto there, when I press A it should go high. And again here. And switch B should go high, and switch B should go high. Okay, so what should happen? This is a comparator circuit. It is comparing 2 inputs, and when the inputs are the same, Q will be high, and when the outputs are different, Q will be low. So at the moment, both inputs are low, and therefore the output is high. If I press one of the inputs low, so they're different, the output goes low. If I press the other switch so the outputs are different, output goes low. And when I press both of them, they're the same, therefore Q should be high. And release. And they're the same high. So our circuit works as expected. This is the end of activity 4. Welcome to activity 5, and we're going to be designing a multiplexer using logic gates. We're going to be designing a 2-to-1 multiplexer. Let's have a little look at the internal workings of a multiplexer first of all and just try and understand what it does. Here we have the multiplexer, and this is the truth table. We have 2 inputs, S0 and S1. We're not going to call them A and B first of all, because we have an additional pin here, which is A, which is an addressing pin. So these are like the select pins, hence the S's, and this is the address pin. And here is our output Q, one output. And there's like a little switch inside, and what we're saying is that S1 is connected to Q, or S0 is connected to Q, so Q will be the same as either of those when they're connected, depending upon whatever A might be. And we're going to say that Q is the same as S0 when A is a 0, or Q is the same as S1 when A is a 1. So Q will be the same as S0 whether it's a 0 or a 1 when A is a 0, and Q is the same as S1 whether it's a 0 or a 1 when A is a 1. So let's have a little look at our truth table now. So what we've got here is our truth table, but it's a bit more complicated than before, and we've also got some don't care states, because we don't care what S1 is when we're working with S0, because it would be irrelevant. Additionally, we don't care what S0 is when we're working with S1. So S0 can either be a 0 or a 1. There are its two possibilities. Likewise, S1 can be a 0 or a 1. Now, A can either be a 0 or a 1. So therefore, let's give it the value 0, and therefore when A is a 0, S0 will follow it, and when A is a 1, S1 will follow it. So, going back to our truth table, we said that Q is the same as S0 when A is a 0. Q output is the same as S0 when A is a 0. So here A is a 0, therefore Q is the same as S0. So in this case, Q will be a 0, and then Q will be a 1. Next, Q is the same as S1 when A is a 1. So where A is a 1 here, Q is going to be the same as S1. So in this case, it's a 0 and a 1. Now looking at the output Q, once again, it doesn't form any relation to a known logic gate. So we're going to have to construct and combine logic gates to create that output. Now we have two zeros in our outputs and we have two ones in our outputs. We could work with either of them, but it doesn't really matter. So we're going to work with the ones. So what we're saying is that we get an output 1 when A is a 0 and S0 is a 1. So we could say this a slightly different way. When the output here is a 1, A is not a 1, and S0 is a 1. Notice the way I use the term AND. So not 0 and S0. So we're going to be using an AND gate here. And the inputs will be S0. So I'm going to take from S0 and not A. Well, what I've done to help you here, I've drawn in a NOT gate. So if this is A, at this point here, it must be not A. So I'm going to take from there and across there. So this output now becomes not A and S0. The dot represents the AND. The bar represents the NOT. Next, let's look at the other one. In this case, the output is a 1 when we have A and S1. It's good that these are don't care states because they don't have any effect on the circuit. So once again, Q is a 1 when A is a 1 and S1 is a 1. So A is a 1, so I'm going to take my A from down here and S1 is a 1. There's a bit of crisscrossing going on, but as long as you can follow your path, that's fine. So this output here is, of course, A and S1. But the trouble is we're now left once again with two outputs and we only want one. We want one output, which is Q. And we can do the same as we did in the previous activity by combining those two outputs into an OR gate. So in this case, If either of these outputs are a 1, then Q will be a 1 because it will be that one or that one. So now what we've got an OR combined with these. Now whilst this might seem quite complicated, it's just an additional bit of information so that you understand. So A, not A, and S0, or A and S1. So we combine those two outputs to create that function. If you don't understand that, it's not too important. So there we go. We have our circuit. All that's left now is to label all our pins. So 1, 2, 3. Now the problem is here we're using a second logic gate, so we have to use the second one in the chip, and we know that this is a 4081. So this is the 4081 as well, and the same one, but now we have to use different pins. So we're going to use pins 6, 5 and 4. Notice they don't go sequentially like these. If you look on your data sheet, you will see that that's what happens. The two inputs are 5 and 6, the output is 4. In our OR gate, which is a 4071, we're going to be using pins 1, 2 and 3. And over here on our 4069 NOT gate, we're going to be using the input pin, pin 1, and the output pin, pin 2. So there we have a complete circuit diagram for this activity. So let's look at the circuit. So we have S1 and S0, we have A, our address, and we have Q as our output. The circuit is on. Is it working? Well, we know that Q is the same as S0 when A is a 0. Now obviously A is a 0 at the moment because it's not pressed. Therefore Q must be a 0 because S0 is a 0. If I press S0 and it becomes a 1, it's the A is a 0 and therefore Q should go to a 1 as well, the same as S0. And it does. Now, if I press A, which I am doing, Q is the same as S1 now. S1 is a 0 because it's unpressed, and therefore Q is a 0. So I'm going to press S1, and when S1 goes high, Q goes high. So now S1 is the same as Q when A is a 1. Going back further and just looking at it again, when A is a 0, Q is the same as S0. So we change S0, and that's what happens. When I press A, and A becomes a 1, S1 becomes the same. Q becomes the same as S1. So therefore it shouldn't have any effect on S0. And as I press it, it doesn't. Likewise, when A is a 0, S1 should have no effect on the circuit. That is our 2-to-1 multiplexer, combining two inputs on the same line going to the same output, but we determine which input we use by the address line. This is the end of activity 5.